When an object is moving back and forth due to a force directed towards a central point, and the magnitude of that force is proportional to the distance from that central point, the object is said to be moving with simple harmonic motion. The object above is attached to an ideal spring and moves with simple harmonic motion across a frictionless surface. Since no energy is leaving the block spring system, the total energy is conserved. At A and C, the system contains only potential energy. At B, the system only contains kinetic energy, and the object achieves its maximum velocity. Because of the conservation of energy, the potential energy at the ends of the oscillation or vibration equals the kinetic energy at the center of the oscillation. The potential energy is 0 at B, and the kinetic energy is 0 at A and C. Since the force on the box is greatest at A and C, the acceleration is greatest at these points. Since the force in the box is 0 at B, the acceleration is also 0 there. When the box is moving in the positive direction, the force is directed in the negative direction. When the box is moving in the negative direction, the force is directed in the positive direction. The force on the box at any given time can be found by multiplying the spring constant times the stretch or compression. The period of any object moving with simple harmonic motion is the time for one full cycle. In the case above, it's the time it takes for the box to move from A to B to C and then back to A again. The period of any object moving with simple harmonic motion is the time for one full cycle. In the case above, it's the time it takes for the box to move from A to B to C and then back to A again. We can see from the equation found on your reference table that the period of an oscillating mass is determined by only the mass and the spring constant. If the mass is quadrupled, the period will be doubled. Notice that the period is not determined by the amplitude. Amplitude is the distance that the box moves from its equilibrium position. In the example above, the amplitude is the distance from B to C and B to A. If we pulled the box to a position beyond point C and let go, the box would have a larger amplitude, but not a larger period. So why doesn't the amplitude change the period? The added speed the box gets by increasing the amplitude is canceled out by the extra distance the box has to travel. The conservation of energy dictates that the potential energy at the maximum displacement equals the kinetic energy in the middle of the oscillation. Notice that when you double the maximum stretch, or the amplitude, you double the maximum velocity and quadruple the maximum kinetic energy. Here's a displacement versus time plot for an object moving with simple harmonic motion. Test yourself and see if you can answer these questions. The kinetic energy is at its maximum value when the object is at the equilibrium position and x equals 0. And the kinetic energy is at its minimum value at the ends where the amplitude is at its maximum value. The position of an object moving with simple harmonic motion can be described using cosine or a sine function, with A standing for the object's maximum amplitude. If the plot starts with an amplitude of 0, we use sine. If it starts at the maximum amplitude, it can be described using cosine. Here is the most useful form of the previous equation. If we replace omega with 2 pi over t, we get the top equation. We get the second equation by replacing 1 over t with f, which stands for frequency. This is the equation on your reference table. The more useful form is the one on the top, but you can change the bottom equation to the top equation by knowing that f is 1 over t, because t is 1 over f. Here's another x versus t plot for a mass moving with simple harmonic motion. The maximum amplitude is the distance from the equilibrium position to the top or to the bottom. The amplitude of this object is 2 meters. The period is the time for one full cycle, and the period is 5 seconds. Since this plot starts at the maximum amplitude and not 0, Cosine is used to describe the x versus t plot. Plugging in the amplitude and the period, we get the following equation. Remember that when x is 0, the velocity of the oscillating mass is at its maximum, and when x is at its maximum, the velocity is 0. If x uses cosine, then the velocity equation uses sine. None of the equations above are on your reference table. Just remember that when x uses sine, velocity uses cosine, and vice versa. Since this x plot starts at the maximum amplitude, its equation uses cosine. The amplitude is 1 meter and the period is 2 seconds. A mass oscillating on a spring also undergoes simple harmonic motion. Take a look at the period equation. What doesn't affect the period of a mass oscillating on a spring with simple harmonic motion? Amplitude, mass, spring constant, or the acceleration due to gravity. Take a look at the relationships between period and mass and period and spring constant. The period would be doubled if the mass was quadrupled. If the spring constant were increased 16 times, the period would be quartered.